Okay, so welcome back to another video. So here we have a contest from the USAMO, the United States of America Mathematical Olympiad of 1996, and this is question 1, and we want to show that the average of the following sample size, 2 sine of 2 degrees, 4 sine of 4 degrees, and all the way up to 180 times sine of 180 degrees. So as you see, there is a sequence involved with the values, and we want to show that the average of everything here is equal to cotangent of 1 degrees. So one can use a bunch of trig identities to actually find the average. Of course, we know like averages is in terms of, adding everything up and dividing by however number of the elements exist in the sample size, just like you learn in a typical stats class. One can use trig identities, but we can actually use some complex analysis. And before we get to applying that method, we can apply Feynman's trig that's going to help things a little better. Well, of course, we don't have a function like define/consider, but we will get to that, and then we can actually show by applying all these techniques that we can actually indeed show that the average is indeed this value over here. So with that, let's actually just get started. So to put this in formulas, in other words, we want to put it this way. We want to find 1 over 90 multiplied by the partial sum from k is equal to 1 and then all the way up to 90 of 2 times k and then times sine of 2k degrees. And it's also worth noting that we can say that we know that 1 degrees is in other words converted as the same as pi over 180 degrees, or pi over 180 in radians. Instead of degrees in the radians, it's my bad. But anyway, suppose that we consider the function, I'll call this capital Y and then some input A. We say that this is going to equal to negative the partial sum of the same indexes. But then we have is cosine of 2 times k and then times a. Then from this, that means that if we just take the derivative, or rather, and then take the derivative and then plug in the input for here. So that means y prime of pi over 80, or 180, then it's going to equal to, so the negative for 1 just cancels out, so we're left with positive. K is equal to 1 to 90 of 2k, then times sine of 2k, then multiplied by pi divided by 180, which is indeed what we actually want to solve for in this situation over here. Well, for now, but then that's considered for the partial sum, but all we have to do is just multiply the 1 over 90 at the end. So we'll save that for the very last thing. Let's actually now get into the real deal. So we can actually convert this entire sum over here as in a form of a exponential, or rather Euler's formula. So we have, we're dealing with imaginary units in this world now, again, complex analysis. So y over y of a, in other words, can be rewritten as the partial sum from k is equal to 1 of the real part. So actually, let me first write this as the real and then write in the input, which includes the, the summation symbol. So the real of the partial sum, k equals 1 of e to the power I, and then let me write that as 2 times I first, and then 2i and then k times a. And then with this, now what I can do is inside I'll factor out e to the power 2ia. But what that also actually adjusts is the indexes as well. It decrements by 1. I don't know if that's actually a real word, but it's okay. So that actually puts us at as e to the power 2ia. And then now we have this partial sum. This is going to be from k is equal to 1 to 89, or 0 actually. K is equal to 0, and then all the way up to 89 of e to the power 2ik and then times a. Now we can apply some geometric series into here, so we can use the geometric series formula over here and then continue forward from that. So in other words, we have that this is the negative real of e to the 2ia, and then multiply by 1 minus e to the power 2ia, and then multiply that by 90, and then since with that formula of the partial sums of the upper limit as well, and we can divide this by 1 subtract e to the power 2i times a, and then from here we can now distribute the 2 to the EIA, and then with further simplification, we'll get that this is the negative real of e to the power I times a, subtract e to the power 181, then I times a, all this being divided by e to the negative ia, and then subtract e to the ia. So with this formula now, so we can actually apply Euler's formula with cosine and multiply with the imaginary unit of sine. So here we're going to have now the negative real of, now let's see, we have e to the power ia, so we have this is cosine of a, and add this with I times sine of a, subtract cosine of 181a, and then subtract sine of 181a, all this being divided by negative 2i and then sine of a. Okay, and so with this now we can actually, not only we can factor out the negative from here, well, not really factor out the negative because, well, specifically because what I can do is I'll multiply an I to both the top and the bottom, so that'll become I squared, and then that's equal to -1, and so that negative sign will disappear. And then 2 sine a is still constant, so I'll actually just factor that outside the real. And to jump another step, I'll actually distribute the negative into the numerators of inside over here. So let's see, we have 1 divided by 2 times sine of a. Then we have the real of the, everything is in terms of, you know, the negatives. So this is going to give us negative I times cosine of a. Then add this with sine of a. I need to move on to the next line since there's actually a little glare over here. So plus I times cosine of 181a, and then subtract sine of 181a. We only want to pay attention to the real part, so anything with the imaginary unit associated with it, we can just completely disregard that. And so everything comes together with the real part, so we'll just, and then so what we have now is this is going to be sine of a, and then subtract sine of 181a, all divided by 2 times sine of a. Okay. And so we can actually just simplify this a little further. So this is going to be the same thing as 1/2 subtract sine of 181a, and then divided by 2 times sine of a. And so that's actually going to be our y of a formula in the simplest terms. So what we can do now next is we will actually take the derivative of y of our function y of a. So we have now y prime of a is going to equal 2. So skipping all this, we know that this is 0, but over here that we actually just apply, you know the quotient formula, the quotient rule. And then, so everything come together so far. So we'll have that this is -1/2 then times sine of a, multiplied by 181 cosine times 181a, subtract sine of 181a, and then multiply by cosine of a, all this being divided by sine square of a. So let's actually now plug this back in for pi of 180, since the whole point is that we plug this back in, that actually gives us to what we want to evaluate over here specifically. That's in layman's terms. So y prime of pi divided by 180, then that means we have -1/2. So I think you get the gist. I just actually, for now, just plugging in all these values over here. So let me actually jump to the next clip. So we plugged in pi over 180 for our input. So let's actually switch that back into degrees. So that's actually not that big of a deal to fix up. So I have -1/2, then multiplied by sine of 1 degrees. Then over here, we're going to have multiplied by 181, then multiply. So we actually use a bit of, symmetric identities with trig functions. So that's, in other words, the same thing as negative cosine of 1 degrees. Then next we have subtract sine of, same thing again, trig identities again. So actually this is supposed to be a plus over here, times sine of 1 degrees. I don't know why I said times, plus sine of 1 degrees, then multiplied by cosine of 1 degrees. Then down below, we're going to have, of course, still going to be sine square of 1 degrees. Okay, and so with everything here, we can see that we can clearly factor out a sine of 1 degrees over here. So that actually will make things a little bit easier for us. So -1/2, then sine of 1 degrees But then also that would have to mean we have a negative 181 cosine of 1, and then add this with cosine, so that puts us back to negative 180. That puts us to negative 180 degrees, but we also have a negative over here, so I'll just distribute that negative. That puts that into a positive, and so then that will give us times 180 times cosine of 1 degrees. Then down below, this is actually going to equal, and then down below is actually going to be divided by still sine square of 1 degrees. I have to make some changes in a second. And so we're basically just about done. So, well, in terms of simplification, there's actually one more step to do after this, but we know where that's going to come from. So the sines will cancel, sine of 1 degrees will cancel. And so that actually just yields us, and then multiply to 1/2. That's actually going to give us 90 cosine of 1 degrees, and then divided by sine of 1 degrees. In other words, we can use the trig identity to say this is just 90 times cotangent of 1 degrees. And then all we have to do is just multiply the 190 into the sum that we just derived and calculated over here. So that all that's left is 190, then multiplied by 90 cotangent of 1 degrees. And so that therefore we have just verified that the average of our sample size, that everything that we just discussed, or given rather, is actually indeed going to equal this value over here, cotangent of 1 degrees, just like that. So there we have it. Yep, that's pretty cool if you ask me.